All right. Once again, continuing on the topic 5, RTL combinational components. These are the components that fit in the RTL design. And the first component we did was the decoder. Now we are doing the multiplexer. Okay, we have seen the multiplexer before, but then this is a more comprehensive look at the multiplexer here. All right, so let's start with that. We're going to be doing everything we did for the decoder, functionality, hardware, cascading, configurability, Verilog, application, and then we're going to do one more thing, and that is using it for random logic. Okay, using it for random logic implementation. So what is a multiplexer? A multiplexer is a circuit that multiplexes one or the other input. Okay, what it means is if the select input is 0, A is going to go to the output. If select input is not 0, it's a 1, then B is going to go to the output. Okay, this is called select, and this is how the A and B are selected and how they are marked as such. For example, the 0 next to A, it means that this is selected when S is 0. Now, the multiplexer I'm showing, A is 1 bit, B is 1 bit, but then if I do something like this, for example, put the multiplexer here, a multiplexer here, another multiplexer here, another multiplexer here, okay, and then the same select. Okay, this becomes my A, 3-bit A, 3-bit B, and then 3-bit output. Okay, this is my 3-bit multiplexer. Okay, instead of drawing all of this, what I'm going to do is show you a multiplexer symbol that has 3, 3, 3, and then just a single S for selecting either A or B. And if these are 8 bits, this is called a quad. I'm sorry, an octal 2-to-1 multiplexer. An octal 2-to-1 multiplexer. That means the two inputs and the output are all octal 8 bits. Quad means the outputs are 4 bits. Each bit looks like this. Okay, look at the S input. The S input, if it's a 0, A is selected. Okay. See, if S is 0, this becomes a 1, A is selected. And if S is 1, okay, therefore B is selected. And therefore this is the structure of the gate level structure of the multiplexer. How do we write it? We write it as such. This is the Boolean expression. This is the Verilog description of it, the tilde S and A, or with S and B. Okay, tilde for not, S and A, or, this is the or, this is the or, this is the or. And the condition operator we talked about with the decoder can also be used here. W is If S is 0, then A, otherwise B. Okay? And if we want to use the Verilog, we have the description for it. We have to use assign. We'll be seeing that. This is a 4 to 1 multiplexer, and then it has S1, S0, 1, 0. Okay? What it means is if S1, S0 is 0, 0, A is selected, B is selected, say 0, 0, A is selected, 0, 1, 0, 1, B is selected, 1, 0, okay, 1, 0, 1, 0, C is selected, and then if it is 1, 1, then D is selected. Okay, 1, 1, D is selected. Okay, this one. I can either build the 4 to 1 multiplexer from scratch, meaning from gates. I'm gonna do that. Or I can build it by cascading these two 2 to 1 multiplexers. Okay, let's build this from scratch. S1, S0. Okay, 0, 0. And then I have 1, 2, 3, 4, 0, 0, 0, 1, 1, 0, 1, 1, okay, and then I OR them together, but then instead of ORing, I NOR them together. I NAND them together because these are going to be NAND, and then this is going to be a NAND. Still giving me the functionality of and ORing. I don't do any active low inputs or anything, or active low outputs. This is still active high, and I am putting in either A or B or C, or I'm putting D and the output. Okay, say this is a 4 to 1 multiplexer. But then I can either do it this way, okay, which is directly out of the gates, or I can take this structure that you see here and cascade these structures. Once again, I'm going to show you, well, I can have NAND gates, okay? But once again, I'm going to show you the same way I did with the decoder. If I cascade these, the resulting hardware will have more delay than if I do it directly like I'm doing here on the lower left. Cascading means that I put an S1 for the upper one. So once again, look at the 4 values. If I have 0, 0. Look, what I'm going to do is I am going to bring in S1 and put it on this side here. okay, because the way I read is S1, S0. And so here I have S1, S0, 0, 0, okay. S1 is 0, so this input is selected. S0 is 0, so this input, the upper input is selected, and therefore A is selected. If I have 0, 1, the lower input of this is selected, while since S1 is still 0, the upper input of the front or the output multiplexer is still selected. If I have 1, 0, then the lower input of the output multiplexer is selected, but then the upper input of the lower left multiplexer is selected, and therefore C goes to the output. Finally, if I have finally, if I have 1, 1, then this is selected, this is selected, D goes to the output, which is the same thing that happens with the circuit that I have over here. So what I want you to do is compare what I have here with what you would get if you take these circuits, 3 of these, cascade them like this, whereas if you do the straight NAND gate implementation, which is actually this, okay? Comparing these two, here I have 2 logic levels and ORs, 2 logic levels, and then 2 logic levels here. Okay, but then what I have, if I do it directly, by the way, again, remember that these are, I can put bubbles to cancel bubbles so that I have NANDs and all NANDs. And this circuit is the circuit on the right hand side is a faster circuit. But then what if I have no choice, but I only have 2 to 1 multiplexers? The good thing about multiplexer is that you can take 2 to 1 multiplexers and build any bigger circuit. You can just put all these multiplexers in a tree structure and come up with whatever large multiplexer you want. And what if I want to make this circuit, the one on the lower left, cascadable? Okay, if I want to make it cascadable, the same thing I did with the decoder. In addition to cascading them like the tree structure I'm showing here, I can cascade them by using decoders as well. In order to make it cascadable, I'm going to add an active low enable. So this circuit is no different than the circuit I'm showing in the lower left, except that I have an active low enable here. The active low enable, if it is, okay, if it is 0, this is 1, and therefore the NAND gates are ignoring the input NAND and doing what their S1, S0 inputs tell it to do. But then if my enable is 1, I get a 0 here. The 0 here will force all NAND gate outputs to become 1. Okay. And therefore the NANDing of all these ones gives you 0. That means if it is disabled, a 0 output regardless of what A, B, C, D input values are. It only works if my enable is active. Okay, an active low means 0. If it is a 1, the output remains 0. All right, so this is a multiplexer with an enable input. how do I cascade these? Well, here what I have is a multiplexer. The whole thing is a 16 to 1 multiplexer. See how I'm cascading this? I'm taking a multiplexer, a 4 to 1 multiplexer with an enable input and an OR gate in front of it. So my slice becomes the multiplexer and the OR gate. I repeat this slice as many times as I want, okay? And then, depending on what size multiplexer I want, I will put a decoder. So here I have 4 of these, and therefore I put a 2 to 4 decoder to select one of these multiplexers. If I were to do a, let's say, for 32 to 1, then I would put, see that slice there? I would put 8 of those slices. This is this slice here. I would put 8 of these slices, and then I would put a 3 to 8 decoder, 1, 2, 3, 4, 5, 6, 7, 8, and then these 8 would be selecting any of these 8 multiplexers, 0, 1, 2, 7 multiplexers. Okay, and then the outputs, each one of them has a an OR gate, which goes like this, cascade like this, and therefore my final output will be coming out from this point out here. Not only that, since I'm using a decoder with an active low enable, therefore if I put a 0 here, the whole thing is enabled, and the output reflects A through P inputs depending on S3, S2, S1, S0 being 0, 0, 0, 0 to 1, 1, 1, 1 selecting P. Okay? 0, 0, 0, 0 is selecting A, but they select A through P only if the whole thing is enabled. The whole thing is enabled when I have a 0 on my enable of the decoder. That's the master enable for this entire structure. If the decoder enable is 1, this is not enabled. All the multiplexers are completely disabled. That means their enables are 1. Remember the decoder how it works, right? The enables are 1, none of them is selected, and therefore none of them are looking at their A, B, C, D, or the 4 inputs, and therefore what you get on the output is a big, big 0. All right, that's a cascading of multiplexer. What I'm showing is iterative logic. What it means is if you make this slice, okay, and then this slice repeat and repeat and repeat, you will have a much larger circuit. These are the various forms for doing the Verilog description of them. Okay, let's do the first one. The first one says use an assign W, which is a single bit, is either A or B or C or D, or if none of them, is an X. Okay, means something bad is happening. If S is 2 tick B 0 0, that means 2 bits, binary 0 0. Okay, or I could say 2 tick decimal 0. Okay, or I could just simply say 0, 1, 2, 3. I could do that. With Verilog, be very specific. Okay, when you say 2 tick B 0 0, you are saying 2 bits, binary 0 0. S is a 2-bit vector, and therefore 0 0 goes to these 2 bits. When you say 0 or 1 or 2 or 3 without any size and the base of the number, it gives you a 32-bit binary number, and then it truncates 30 of them and gives you only 2 bits. So why bother? Why not specifically say I need 2 bits and these are the 2 bits I want? And so assign W is either A or B or C or D, depending on S being 0, 1, 2, or 3. Let me go back to my decoder. Decoder is correct. A is equal, but then here there is an error. This has to be equal. Okay, so S equal to tick P10. Okay, two equals connected. All right, that's one way of doing the description. Another way of doing the description is this one. This is an interesting one. I'm using curly bracket. Curly bracket means cascading. I'm cascading A, B, C, and D together. That forms a 4-bit vector. So J is a 4-bit vector. Okay, and the 4-bit vector J consists of A, then B, then C, then D. Okay, and then I take S, and index J. So J is indexed by S if S is 0. Okay, this should have been 0, 2, 3. Okay, if S is 0, then leftmost J, which is bit 0, which is A, would go to the output. Doesn't matter, it still works, but then to correspond this with what we had, that means S0 selects A, you have to reverse the J indexing. And so what I'm doing here, which is a good format for a selection, is you are saying my W output is J indexed by S. S is a 2-bit number, 0, 1, 2, 3, 4. I'm sorry, 0, 1, 2, 0, 1, 2, 3. Okay. And therefore you will be selecting one of the J elements which you formed on line 10 using assign. There is one more way of doing this, and this way, if instead of your inputs being a scalar, A, B, C, D, E, F, G, H, 1-bit input, if you vectorize all your inputs together, so if you have an 8-to-1 multiplexer for, look line 13, input 7:0 J. That means J is an 8-bit vector, and then simply use J indexed by S, which is a 3-bit number. Select input 3-bit, and therefore these 3-bit will be selecting one of the J's, and then the J's are the 8 inputs of the multiplexer. So instead of A, B, C, D, E, F, G, H, you have J, 7J, 6, 5, all the way to 0 as the inputs of your 8-to-1 multiplexer. This is 8-to-1 multiplexer. This is your W. This is S2:0. And then these are your inputs. J, 8-bit vector. And then you're taking J, bit by bit of it. Okay, bit 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7. Okay, something like this. Whereas this upper one is 1, 2, 3, 4, A, B, C, D, and S is 1:0. Okay. And the actually the first one also the same way, 1:0. All right, so this applies to this and this. Fine. Then what you have is, I'm going to do one more way of doing this, and this one would be Boolean. Okay, not very compact. Okay, but I'm going to take this and do assign W equal. Okay, S1 ended with S0 ended with A. That means if S1 is 0, S0 is 0, A, or just write down everything. 1, I'm going to write the whole thing, 0, B. Okay? Just write complete Boolean expression. This is actually the same Boolean that we have over here. Okay, and notice that this one doesn't have an enable. If you want to have an enable like this one, also add an enable to each of these product terms. Okay, and once again, this is A, selecting A, selecting B, selecting C, and finally selecting D. That's a Boolean representation. All right, this is good with the multiplexers, and we have seen the Verilog, we have seen cascading, we have seen application. Application is this. For example, if you have several sources and you want to select one of those sources to go on your bus to go into some other system, so you put multiplexers there. So you have source 1, select source 1. Source 2, select source 2. Okay? And therefore, each of these have their own select inputs, and they will be selected to go on a, let's say, shared bus. There are a lot of other uses of multiplexers. Multiplexers are used for when you have serial data trying to, parallel data trying to send them over on a serial line. What you do is you take a multiplexer. Okay, let's say you have 16 parallel data, and then you have a 16 to 1 multiplexer, and the S input goes from 0, 0, 0, 0, selecting the first one, then selecting the next one, and therefore all of these parallel bits will be serialized on this serial data line. Okay. One more thing we mentioned, and that was multiplexer-based design. Okay, so let's leave that for the next part.